Okay. Now we can get started. So acids and bases are going to be on the next exam, exam 4. And they're split into 2 chapters. We're going to cover both of them today because we're not going to have a lab. So we got enough time, I hope. Okay, let's start with the basics.
Pretty much 3 hours.
Huh?
I said pretty much 3 hours to cover both chapters.
Yeah, could be.
I'm surprised there's like literally 20 pages.
So 20 times 6 is 60 slides.
Yeah.
Okay, one of the earliest concepts concerning acid and bases was proposed by Arrhenius. He said that acids are anything that produce hydrogen ions in solution. Right? So he would say that this would produce that in solution. And we're talking about aqueous solution now at this point. He also said that bases, these are acids, bases in solution produce hydroxyl ions. Oops. Sorry, my mistake. Okay. So that was Arrhenius' definition, and it worked pretty well. We know how to characterize acids and bases based upon their behaviors, even how they feel or how they taste. Acids are going to be sour. Bases are going to be bitter. Bases will also get some on your hand, and you rub your fingers together, it's real slick. The problem came about when solutions were identified that were basic, but you couldn't identify a hydroxyl in the mother molecule. There was no hydroxyl in the molecule. Right, so this was Arrhenius, 2 R's. So here's an example of a base that in solution produced hydroxyls in the solution, and there are no hydroxyls in it. Right? So the explanation for that is when it goes into solution, a proton is transferred from water to this species and makes this one. And if you take one hydrogen away from that, what do you got left? Hydroxyl. Okay. So we needed a new definition, and that was proposed by Lowry and Bronsted. Well, Bronsted was a foreigner, but so was Lowry. So their concept was that they based their acid-base definition on the proton only. So they said an acid was a proton donor, and a base was a proton acceptor. So with that definition, ammonia is a base because it accepts a proton from water. Well, okay, like any theory, it has limitations. The Bronsted-Lowry model incorporates Arrhenius, except with the exception that the molecule may not have hydroxyl built into it. We're going to get to another model that allows us to identify acids and bases in non-aqueous solutions. But as far as the solution is aqueous, this definition holds. Because you got lots of water molecules in there to play around with. Okay. So with the Bronsted-Lowry definition, hydrochloric acid in solution reacts with, well, hydrogen chloride gas, if you bubble it through water, reacts with the water. It's the acid, water is the base, because it's the donor, this is the donor, this is the acceptor. So what that tells me is that water can either be a base or it can be an acid. It can be it can donate a proton or it can accept a proton. Okay. In this case, water is accepting a proton, and it produces this species right here called the hydronium ion. Okay, so these reactions, another characteristic is also that these reactions are reversible. They go both directions. Which you should recognize as a lead-in to equilibrium. So acids and bases have equilibrium constants as well. And we'll get to those eventually. Okay, so this is just an animation. So you expect me to, I got to get it again. Right, so there's a tug of war going on for protons in solution. This is your ammonia molecule, and it's trying to receive a hydrogen atom, actually a proton, because it leaves the electron behind. So it's just the proton that goes over to the ammonia molecule, makes the ammonium polyatomic ion. And since it's positively charged, makes this one +1, and the electron stays behind and make this the -1 hydroxyl. Okay, same thing can happen to water. Right? Water can react with another water molecule. And if it does, one becomes the base and one becomes the acid. So let's say this is the base. It's going to accept a proton. So one of these protons is going to be transferred over here and give us the hydronium ion and leave behind hydroxyl. And in water, in pure water, in anything aqueous, that reaction always happens. Okay? No matter what else you put in there, this will always take place. Oops. Got a video going on.
The Bronsted-Lowry concept defines acids as proton donors and bases as proton acceptors. In the reaction of aqueous hydronium ions and ammonia molecules, the hydronium ion acts as the Bronsted-Lowry acid and the ammonia molecule as the Bronsted-Lowry base. The net effect is that of a proton transfer from hydronium to ammonia, forming water and the ammonium ion.
Just so you know, the balance or the equilibrium in this reaction is heavily favored in that direction. It wants to be this, not that. There's a little little bit of this, there's a whole lot of that. Okay.
Let's go to the left.
Yeah, it prefers to be over here. We'll say more about that later. Okay, so more definitions. So we use, that's our generic acid. Remember, and from our nomenclature study last semester, anything preceded by hydrogen, you can suspect is going to be an acid if you put it in water. But when you put it in water, it wants to react with other water molecules. So we have aqueous solution. And this hydrogen is going to be transferred over to that water and leave behind this species. So when that happens, this is the acid. Water now is a base. That's the acceptor. And this produces that, which is the conjugate base. Why do we call it the conjugate base? Because it was produced from an acid. But now it has the ability to accept a proton, which means it's a base. Okay. So it's the conjugate base of that acid.
And that would be conjugate acid receiving that conjugate base.
Right. That becomes the conjugate acid of this base. Okay? Just definitions.
So if we drew a line, that one would connect with that base to that base. Or
This
that
one,
acid to that
this one
base.
produces that one.
That's the left acid goes to that base.
You go like that by a loss of a proton. Okay? And this one goes to that one by a gain of a proton. Okay? Now, acid-base reactions are like redox reactions. They always occur in pairs. An acid reacts with a base. Acid never happens alone. So if you've got an acid and you're describing a reaction, there has to be a base, something to accept the proton. Or if you have a base, there's got to be an acid to donate the proton. So these reactions can go backwards and forwards. And it depends upon whether this is a strong acid in chemical terms or a weak acid. Right? A strong acid says that it's going to completely dissociate. Nothing left over of this. So that means it's basically going all the way to this side, to completion, producing all of the conjugate base from that acid. And examples, hydrochloric acid.
On ones with the H, most of the strong acids.
Mm-hmm.
Is that the opposite?
No, it's an acid, yes. But they're not all strong acids. I'm giving you some examples. Hydrochloric acid, nitric acid, hydrobromic acid is strong. Let's see.
They're hydrochloric.
That is hydrochloric.
Cool.
Oh, hydrochloric.
Yeah.
Interesting, you should say something. It's weak. They get stronger as you go down. So that's weak. This is strong with its hydrogen. Strong, strong. So this one would be strong also. This one is strong for the first proton. Right? And I'll say more about that later. When acids dissociate, they do so one proton at a time. They only have one proton, that's the end of the story. They have two protons, then it gives up one proton first, under a certain equilibrium situation. In this case, the equilibrium is all the way to the right, producing, well, that. And this. Okay? So acid reactions occur one proton at a time. Like I said, I'll say more about that later. But these are all strong acids, and they completely dissociate. Strong bases, just take any of your alkali metals. That's a strong base. This would be an Arrhenius base, right? Because it's got hydroxyl built in it. This one. Let's see. Yeah, probably this one too. Okay. Now this is in chemical terms, right? When we say strong, we mean that in aqueous solution, the molecule completely dissociates. There's nothing left of that.
Do the bases get stronger as you go down or weaker? Or does it like just vary?
No, there's a trend. Let me stop and think a second.
Because you're going down when you got to rubidium, and then you were like, this one should be too. So you weren't like.
And it gets stronger this way. I'm not sure about that. I should know. Think about it a few minutes. Okay. Maybe it'll come out in the discussion.
Acid ionization in water is an equilibrium reaction. Acetic acid ionizes in water to a small degree, forming hydronium and acetate ions. Because of the small degree of ionization, and because water is nearly a pure liquid, we rearrange the equilibrium constant expression. If we now remove water from both the chemical and equilibrium equations, we get the acid ionization constant for water. The Ka for acetic acid is 1.7 times 10 to the minus 5. The animation sequence shows acetic acid reacting with water to form hydronium and acetate ions. At equilibrium, both the forward and reverse reactions proceed at the same rate, such that the net concentration of each ion remains constant.
Okay, so we have acetic acid, and then it reacts with water. That's a pure liquid. This is an aqueous solution. And it's in equilibrium with this proton transferred to that water. So this is the acid, that's the base. This is the conjugate base. Get ahead of myself. That's the conjugate base of our acetic acid. That's the acetate ion. And it's in solution. And then here's our conjugate acid.
Are we still going to take? Oh, never mind.
Okay, so when you write the equilibrium expression, there's a solution, solution, solution. You keep those three. There's a pure liquid, throw that one out. It doesn't become part of the equilibrium expression. All right, so products.
I feel like it's a kind of off balance though.
All right, so that's your expression. What's the problem?
Wouldn't that go like, I know that there's like H3O on this side.
Mm-hmm.
And we have water right there.
Mm-hmm.
But wouldn't there'd be like,
This is usually low concentration, but not always. That plus is kind of misleading. Let's put it back there.
because on this side there's, you can't all the H's are like,
Well-
6 H's.
The constant is 10 to the minus fifth, which means you got very, very little of this stuff over there. Right? Sometimes you'll see it quoted as 1.8, 10 to the minus fifth, 1.7. But it's still very small amount here, very large amount here. So the equilibrium is over here.
I have a question. Is that just this 1.7, I assume the negative is the amount you didn't solve?
Oh yeah, you had to solve it to get the original value. But this is something you can look up in a reference manual. Right, K value. Ka means the acid dissociation constant. In other words, you've got an expression, an equation that starts with an acid. And it has to be a weak acid because the K value for a strong acid means nothing. Right? Because it's all over here and nothing over here. K is virtually infinity. So it needs to, this is only valid for weak acids. And pure liquids are not part of the expression. If you want to think of it in terms of what happened to it, well, if we put it over here, it would actually be buried in this value. It doesn't change. We only want values that change to establish equilibrium. They need to shift. We start off with this, you just put it in pure water, some of it's going to go that way. But the water is so concentrated that it will not change. Okay? In fact, it's in the neighborhood of 40 or 45 molar. So it's just huge compared to the rest of them. Okay, so this is a weak acid. Strong acids, I said before, the equilibrium lies to the right, almost totally. You might get some of a strong acid over here, but not enough to be concerned with. Now, the other thing that you see is what is the nature of the acid and the conjugate base? How are they related? Right? If this is a weak acid, and it does not want to give up that proton. Right? It will if coerced. Right? It encounters a water molecule, so it gives up a proton occasionally. But when it does, it produces this conjugate base. Now, if you think about the strength of attraction, what is it that keeps that a weak acid? It's some attraction that holds the proton there. So if you produce the conjugate base, how is it going to be in relationship to protons, available protons? It's going to be a strong attractor, right? Because it wants to be there. It doesn't want to be there, right? So that means weak acids produce strong conjugate bases. Okay, and vice versa. Weak bases produce strong conjugate acids. So if we consider this one, giving us these species, that base produces this acid. That's a weak base. Right? So the K value for this reaction will be very small. This is the conjugate acid of that base, which makes it a strong acid. This is a weak base, strong acid. It wants to give up that proton, which makes it a strong acid. Okay? Just remember that rule of thumb. Weak acids produce strong conjugate bases. Weak bases produce strong conjugate acids. And strong acids produce weak conjugate bases. All right, for instance, for this reaction, okay, for this reaction, that's a strong acid, so it produces a weak base. That means that this species does not want a proton. It's a weak base. Bases are proton acceptors. A weak base means it does not want to accept a proton. So a strong acid produces a weak conjugate base. And you can order them, right? If you have something that's 10 to the minus 5 here as an acid, and you have, say, something that's maybe 10 to the minus 10, that means it's a weaker acid, which means it produces a stronger base, conjugate base. Okay. So we can do some ordering. We can say something qualitative about the strengths of acids and their conjugate bases. All right. Well, that's not going on. All right, so this came straight out of your book. If the Ka is large, in fact, if the Ka is infinity, you have a strong acid. But when we say Ka is large, I suppose you could say Ka of, I don't know, 5, 10, 20, 30, right? Would basically put things over there. If the Ka is small, you have a weak acid. And where's the position of the dissociation, right? It's far to the right for strong and far to the left for weak. The equilibrium concentration of now here's the convention. This is actually what happens. Protons never exist. This is the physical truth. Protons never exist as separate protons in a solution. They're always associated with something. They're either attached to their original acid or they're attached to a water molecule as a hydronium. Okay? But for calculation purposes, we could just as easily say this yields that plus that. And you get the same value. Right? This concentration, would it be equal to that concentration for calculation purposes? So when you see these values, the equilibrium concentration of protons, the reality is those are hydroniums. Okay? And there's some instructors that refuse to write it this way. But history is against it. Because it's easier to write just the hydrogen, the proton, right? And some of the calculations and expressions that come out of acid-base chemistry don't have the hydronium. They just have the proton in their definitions. Right? So I just wanted to make that clear. This is physical reality, but this works just as well for calculations. Okay, so if you have a strong acid, you're going to get a weak conjugate base, or if you have a weak acid, you get a strong conjugate base. All right, let me leave that there just in case. We're going to have the next one. Okay, I mentioned this earlier. Water will react with one of its neighbors. If you have pure water, it will react with one of its neighbors and transfer a proton. Right? So one is the acid and the other is the base. And you set up an equilibrium where you produce the conjugate base of the acid and the conjugate acid of the base. Okay. These are in aqueous solution now. These are both pure liquids, right? So the K with a special subscript for water equals that concentration times that concentration. Usually it's written this way. And these don't appear because they're pure liquids, right? So all you need to know is this concentration, that concentration, and you can calculate a value. In fact, since it's 1-to-1, if you know one of them, you know the other one. All right? So if we say at 25 degrees Celsius, the concentration of this one is 1 times 10 to the minus 7, and this one has to be 1 times 10 to the minus 7. If it's pure water, that's the only thing you've got in the beaker. One came from one came from the other, and they have to be equal because the ratios are 1-to-1. So if we just plug in those values, multiply them together, the KW for pure water at 25 degrees, pretty close to 25, is 1 times 10 to the minus 14. Okay. So that means that it's a very weak reaction. You could look at it and say this is a weak acid or that's a weak base. Doesn't matter. They both dissociate the same way. They both accept the same way. So this weak acid produces this strong conjugate base, or this weak base produces this strong conjugate acid. And what happens is, since this is a strong base, and that's a strong acid, this one wants to give its proton to that one, which readily accepts it and keeps everything here, largely, to that ratio. To that product, excuse me, that product. And that reaction always happens in water. In aqueous solutions, this reaction is always happening. No matter what else you put in there, this one has to be considered. Okay? You can, and that's, one term for that is autoionization. If you have pure ammonia, right, like if you were a farmer, you had anhydrous ammonia in your stainless steel tank sitting behind your tractor, and behind the tank, you're pulling an injector bar, right? The ammonia is being injected down into the soil, because once it comes out of that tank, it instantly turns to gas. So you want it underground where it can react with water. Right? In the tank, it's doing this. It's producing these two. Right? But when it hits water in the soil, you want to get it down below the moisture line. Once it hits that water, the reaction of ammonia with water gives you ammonium ions plus hydroxyls and produces a microbial kill zone like that initially, and then the microbes reinvade as the concentration of ammonia decreases and spreads. Then the microbes come back in, convert that ammonia to nitrates, then the plants can take them up. You usually don't put it in there. The best time to put it in there is before you plant. Give it a chance to react, then go in and plant. Or have your rows far enough apart and put your injector precisely in the middle before the plants have a chance to develop a lot of root system, because once that ammonia hits that soil, it's going to kill any roots that touch it. So there's a science to it, put it that way.
It's like with some people, like fertilizers, This is where I have chickens and like chicken, put it in plants. So there's chemical burn.
It'll burn.
Yeah.
Yeah.
That you have to
They
wait
produce a
like,
chemical burn.
like a year for it.
Now, with poultry, that's part of their nitrogen waste, which is a fertilizer. But fishes and some reptiles get rid of their excess nitrogen as ammonia.
Through their year.
Yeah, through their urine. Right, and they can do it because they've got lots of water going through their system. Ammonia is toxic, right, in very small amounts, so they have to get rid of it. You can't hold ammonia in your bladder. Right? The fish have bladders, but not urine bladders. They have swim bladders. It's a different thing. So now, once you get to land animals that really don't care about weight, right, you convert this to urea. Right? And urea is a molecule that has two ammonias attached to the molecule. So you can, and it's liquid, right? And it's water soluble. So you can store it in your bladder until you get ready to eliminate. And it doesn't take as much water. So for land animals, that's important because we can't afford to throw away water. But it's less toxic, much less toxic. For birds and some reptiles, they produce uric acid. Now, I can't remember exactly how this, it's got, instead of 2, it's got 4 nitrogens per molecule. And I think it's, it's got a nitrogen here. It's got a nitrogen here, I think. One here, 3, maybe another one over here. So it's got 4 nitrogens in the molecule, and it's a solid. So that's important for birds, especially. I mean, if you're going to fly, you want to concentrate it into as small a mass as possible. Right? The liquid adds too much water to the mass. This is less toxic because it's a solid. And that's the white stuff that comes out in bird poop. So their poop comes out with brown and white in it. The brown is what we consider feces, and uric acid is the white part. But once it starts breaking down, and it is an acid, so once it starts breaking down, it's very concentrated. Right? So it can burn cells. Plant cells in particular.
The white stuff's what's burns on the actual.
Yes, yes. So what you have to do is let it age. Composting is best. And let the microbes get at it and convert it into nitrate and ammonia compounds that are less toxic. So farmers will fertilize with anhydrous ammonia, or they'll fertilize with ammonium nitrate. Right? They can still get hold of large quantities of ammonium nitrate. It's just regulated for obvious reasons. 6% fuel oil in ammonium nitrate makes a nice little bottle. And they still use it in the mining industry, right? AMPO. They'll put a stick of dynamite in the bottom of the hole and overpack it with ammonium nitrate. And when they set off the dynamite, it just magnifies the explosion cheaply. Right? The stuff is dirt cheap compared to dynamite or TNT or whatever they use. And they also fertilize with urea. You can buy urea prills. Right? They're just white. They're both white. This one, the urea, they're both white. But this one is 34%, by weight, nitrogen. And urea, I already drew the molecule, is 46%. So it's more concentrated too. And urea cannot be used as an explosive. Well, I digress. So this happens with water all the time. And here's a description, right? No matter what the solution contains, the product of hydrogen and hydroxyls in that solution must always be 1 times 10 to the minus 14. And this is why it has to be that way. So if you add extra hydrogens, they're going to enter this reaction and deplete the hydroxyls to reach equilibrium. Right? So when they do that, you add hydrogens, say in a strong acid, and they'll react with the hydroxyls that are produced, or they'll react with the water molecules, but the balance is still the same. And we'll work some problems that use the addition of acid or base. So, if you've got pure water and you have these concentrations, this one is equal to that one. This is a neutral solution. It's neither acid nor base, right? Because they're equal. You don't have an imbalance. You don't have excess acid. You don't have excess base. It's neutral. But if you have a situation now where it's not just water, but you have an excess of hydroniums, or protons, with less hydroxyls, then you have an acidic solution. So in that case, you have an increase of that one and a decrease of this one. And the other way around, you have a decrease of this one and an increase of that one. You have a basic solution. Okay, that's sort of semi-quantitative approach. One of these is acid. The other is the base. This would be the conjugate base of the acid, and this would be the conjugate acid, the base. So whenever you have an acid other than water dissociating in aqueous solution, you would incorporate the conjugate acid times the conjugate base concentration divided by the undissociated acid concentration. And that will give you your K value for that acid. Okay, if the equilibrium lies to the right for this reaction, right? If it lies far to the right, then what can we say about the K value? It's going to be large, yeah. It may not be a strong acid, but it'll be large. Usually greater than 1. Simply because with acid dissociation constants, we're only doing 1 proton at a time. So the coefficients are going to be 1 to 1 to 1 to 1. Okay. And if it's the other way around, it's less than 1. I've got to mute my phone. Hold on a second. Jump calls. Okay. Stop that nonsense. Okay. If water is better base than A minus, what can we say about this reaction? So look at it this way. What do we mean by water is a better base than A minus? That means water has a stronger attraction for protons than A minus does. So if this one has a stronger attraction for protons than that one does, this one's going to take protons from this species and produce more A minus than this one. So the products should dominate in that situation, where water is a stronger base. Okay, everybody got that one? All right. So what does this mean about HA? Is it a strong or a weak acid? Yes. Exactly. So HA is a strong acid. So what about the value of Ka? Greater than or less than 1? Should be greater. Yep. Okay, you guys are catching on. So what if we have a 1 molar solution of HCl? Let's see what happens. Let's see if we can say something about, let's order these from strongest to weakest base. So if we look at them in terms of the origin of their acids, HCl is a strong acid. So A minus should be a very weak base. Well, wait a minute. No, that's not right. This is from a weak acid. So this would be a very weak base. So it would be the weakest. That means it would be on the right, because we're going strongest to weakest. This would be the weakest base.
Why is it?
Because HCl is a strong acid. So chloride ion would be a weak base. And then if this is from a weak acid, it would be a very strong base. And water would be in the middle. Right? Oh, here's our logic. Right, so from strongest to weakest base, this one would be the strongest base, this would be the weakest base. Water somewhere in between. Right, so those are easy when you got those 3 choices. So suppose rather than put an acid or a base, we use a salt like this one. Right, so there's our minus, there's our plus. If we put that in solution, sodium's not going to react with anything. Our focus should be on this species. So this species, sodium is a spectator. This species reacts with water.
So we just ignore the spectator ion.
Yeah, it's a spectator. Okay, so this is a liquid, and these are all aqueous solutions. Okay. So if we're given that A minus is an anion originating with a weak acid, so the origin of the A minus is from a weak acid, that means A minus is a strong base, right? So in this reaction, when we put it in solution, it's going to have a strong attraction for protons. Right, so it's going to take protons from water and drive the reaction predominantly over here. Okay? So that means when you put a salt of a metal and the conjugate base of a weak acid, which means it's a strong base, When you put that in solution, then this behaves independently of its origin. Don't consider that. That's just where it came from. But when you put it in solution, now it wants protons, and it can't get them from the protons that were produced by the acid, right? Because there's none there. It has to take them from water. So this strong base takes protons from water and produces predominantly product, right? So that means you have a basic solution. You have excess hydroxyls. So the equilibrium is going to lie. That's wrong. That's the way the authors, the producers of the slides, they got it wrong. It's to the right is the way the equilibrium will lie. Is the value of Kb. Now in this case, we don't have an acid over here, do we? Right? So we can't say Ka is our equilibrium expression. Our equilibrium expression is actually Kb, the K for the base. Right? So our equilibrium expression is going to be this acid produced. So we do get some of that. And the hydroxyl divided by concentration of components. And water doesn't count. Right, so that's our expression. Is the value of Kb greater than or less than 1? It would be greater than 1, because we're going to produce lots of that. So we lose this because it doesn't want to be that way. It wants a proton. So this is small, these two are large. The value is going to be greater than 1. Okay? Does this mean A minus is a strong or a weak base? It's a strong base. Okay. So before we had comparisons of only 3 things. Now we're going to complicate it a little bit. So we have these 4 species, arrange them from weakest to strongest base. Okay? So if we have water, chloride, cyanide, and acetate, okay? Consider where they came from. Right? This came from a strong acid. So it would be a weak base. Okay? These two originated from weak acids. So they would be strong bases. What we need to do determine is what is their relative strengths.
C would be stronger because acidic was weaker originally than acidic.
Yes, this is a weaker acid than HCN is weaker than HC2H3O2.
So that would mean it would be the stronger base.
Right. This would be the strongest base. So weakest to strongest, we can put this one out here on the right, and we can put this one over here as the weakest base. Right? That's the weakest. That's the strongest base. Now what we have to do is decide what's the relationship of this one to that one. Okay? So if you look at the K for water, right? This species has a K value of 10 to the minus 14, whereas this one was derived from a K value of 10 to the minus 5. So 10 to the minus 14 here. This one was derived from 10 to the minus 5. But that's for the acid. right? And we haven't talked about how to calculate the Kb from the Ka. The Kb of this based on the Ka of its acid. So we're going to have to sort of intuit it. So which one would be stronger in terms of accepting a proton? Actually, the stronger one in terms of accepting protons would be this one. Because with this equilibrium, we produce 10 to the minus 7 as a product. And with this one, we produce 10 to the minus 5. Right, so it should be stronger in terms of attracting protons. Right. That's for the acid form. So we have to sort of say, okay, if this one is 10 to the minus 5th and this one's 10 to the minus 7 for its basic species.
That one would be lower.
Right.
Okay, I see.
Right. So the water would come first and acetate would come second. Now there's a way to quantitatively justify that. But I have to show you how to calculate the Kb first so that you can compare the Kb of this with that value. Okay. Now, what do you do when you've got an acid reacting with a conjugate base of an acid? The idea here is to compare the Kas. So for the HCN, is 10 to the minus 10, is its Ka. The Ka for HF is 10 to the minus 4th, so it's on this side. So what's the drive? The drive here is to give up protons to go that direction, and the drive here is to give up protons to go this direction. And what we find is the value is larger for this one to dissociate than it is for that one. So we should expect the reaction to go back this direction. Right? When we consider that producing this and that, or this producing this and that, with this one is at 10 to the minus 10, and this one is 10 to the minus 4. Right? So there's competition there. This one has a drive to make protons to that extent, but this one is even a stronger 10 to the minus 4th, is 6 orders of magnitude stronger to produce these values here than this one is. So what that tells me is this one is going to win in its reverse direction. Oops. Oh, okay, here's the explanation. What does each one mean? Well, the Ka for HCN is very small. It's just the strength, it's a strong drive to remain this. Whereas HF has a stronger drive to return to that side. We would reverse the reaction, go. So the strength is to go to this one on that side of the reaction. So it wants to push it back that way. And HCN is only too happy to let it do it. So you can look at it in two different ways. Either HCN wins in its attraction for protons, or HF wins in its drive to give up protons. but the reaction wants to be on this side as written up there, not like this. That's confusing. But this reaction is going to be predominantly reactants, so your K would be less than 1. Any questions before we get to calculated KB? All right. So let's learn how to calculate a KB if you're given a KA. So this would be our abbreviated form, right? Instead of hydroniums here, we're just going to say this dissociates into that and that. Right? We know it reacts with water, but the calculations are the same because water disappears anyway. No, not for calculation purposes. We could put water in there and we could put hydronium here, but that water is going to drop out anyway, so the expression is the same. So there's our Ka for that acid. Now, what if we take this one by itself and react it with water, right? Suppose we add it as a sodium salt, a sodium A, to the solution. Now, this one starts the reaction. It's not starting here, it's starting here. That's going to react with water and produce this acid plus hydroxyls, right? So what's the expression there? The Kb for this, because we're producing a base, is this one times that one, these are products, divided by that. Right?
So did you just take the A from the original formula and just bring it down and just react with water?
In a manner of speaking, but we don't, this has a different starting point. We're only interested in this one as our starting point, not that one. Okay, so how do we get it into solution? Like before, we just put it in as an alkali metal salt. That's a good way to do it. You're only interested in putting this one into solution with no acid added, just that anion, the conjugate base. That's all you want to start with. You don't want any of that in there to start with. So when you start with this one, it reacts with water and produces a base, plus the conjugate acid. Right? Okay, so the expression for that one is products divided by reactants with water disappearing again. How are they related? Well, if you add these two expressions together, right, which we can do, right, based on Hess's law. So you add them together, those cancel out, those cancel out, and what you get is water dissociating into protons and hydroxyls. You get the water equation, right, where Kw equals, that should be a times, Ka, where Kw equals this one, right? So when we add these together, right, what do you do when you add two equations together? You multiply the equilibrium expressions. So if we multiply this one times that one, that cancels, that cancels, that cancels, that cancels, and you're left with your water expression, right? So this Ka times Kb equals Kw, which is that. So all of that was provided so that we could say Ka times Kb equals Kw. Right? So with Kw being 10 to the minus 14, if you know what Ka is, you can solve for Kv for that, for this reaction. Right? If you have this type of reaction, but you don't know what the Kv is, you only know what the Ka is for this species, then you can calculate what the Kv is simply by dividing the Ka into Kw. Okay? The whole point of this, well, one of the points of this is for you to avoid saying, if I know the Ka, all I have to do is take the reciprocal of it, and I got Kb. You don't, because it's a different reaction. The reverse reaction, yeah, the Ka. Reverse reaction for this one, the K would be the reciprocal, right, based on our rules. But it's not, this is not the reciprocal of that. You have to use this expression to get your Kb. All right? And we're always going to use 1 times 10 to the minus 14 for Kb.
Will we always use its base form or yours?
Yeah. So now that we have this reaction as the possibility, what is the K for that reaction? Well, we've got two things involved. We've got this Ka value, plus we have a Kb for this one to produce those. So here's one possibility. You can break the reaction into its individual acid and base forms. Well, there's the acid form and there's acid for HF, but that one has to be reversed, right? So if we just use our typical, Hess's law, we can add two equations together and get our target. And we know that the Ka for this one is that. The Ka for that one's that, but that's not going to do us any good. We need the inverse of HF. So what we're really interested in is how does this one react to produce that? And for that one, we need not the inverse, but the Kb. Right? So that's the trick in this one. You can't take the inverse of that. It says inverse, but that's not. It's the inverse reaction, but this is extracting H from water, and this is donating H to water. That's the problem with this one. It doesn't include water in the formula, but water is there. And the Kb for this reaction is going to be 1.4 times 10 to the third. Now we can put them together. Well, here we go. When we combine the two reactions, the hydrogens disappear, and the K for the reaction is the Ka for this one times the Kb for that one. So the K is actually 8.6 times 10 to the minus 7 for that reaction. Question?
They already solved it for us, correct? But they already got the 6.2. All that. So.
Yeah, this one, you didn't have to change this one at all because it's based upon that molecule dissociating right there. This is the one you had to calculate, Kb for. We had to know the Ka for HF. Then calculate the Kb because this is the one that's reacting. So this one stands as is, Ka, and this one is calculated from the Ka for that species. Then you can multiply them together.
Could you repeat the reason why why we use water in that formula for the hydride?
Let's back up.
I already said it, but I'm just slow.
It'll let me back up. There we go. Well, we know that in aqueous solution, water is going to be in here. This is going to donate a proton to water. This one's going to extract a proton from water. So you actually have two different reactions here. This one would normally produce that. We don't have that. We have this reacting with water to produce that plus that. And when we add the two reactions together, this is the one that gets added to the HCN, producing hydrogen and cyanide ion. That's why for this one we have a Ka, but this one is the one that we need, the Kb. We need the Kb for that reaction in order to add them together. So we calculate the Kb here. And in that case, this is oversimplified. It leaves the water out. Okay, so that's the problem that you're experiencing. We should have written this one in terms of, okay, if we're starting from that, the reaction we really need is this one. Right? And if we have that one, we need this value, not that. This is the Ka, this is the K. Why does it do that? Wait a minute. It is taking the inverse, isn't it? Well, whoa, 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 whoa. I'm not sure if that's right. What if we write our equation this way, and we write the HCN separately? Right, to do this, okay, we know the K for this one is 10 to the minus 10. For this one, do we get our target reaction? Right, so if we bring it down, HCN plus F minus plus 2 H2O, right, one there, one there. And then, let's see, let's put it in the same order they do, CN, and then HF, and then we get H3O plus and OH minus. Right? So if we put these together, what do we get? We get two H2Os, don't we? All right, we get an H2O here, transfer hydrogen over here, get another H2O. So those cancel. So that does add together. So what we need here is a Kb equal to 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4. Okay? So where's my calculator?
You get that.
1 exponent 14 change the sign, and divide by 7.2. I get 1.4 times 10 to the minus 11. Then we add these together, those two are multiplied. Okay, this tells me that the K for the reaction is 8.6 times 10 to the minus 20. Which means what? That's telling me that our original determination that it would be predominantly over here is true, because that's very small. But it doesn't tell me this. 10 to the minus 7. Tells me 10 to the minus 1. All right.
The calculator they gave me,
I see a problem, huh?
whenever I did the, they gave me that, but they only did
10 to the 5th. No.
Is by the,
1 divided by 7 is about 0.14. And then plus 4 and minus 14 is minus 10. And then move the decimal one more is minus 11. So it should be minus 11. All right, I need to work on this. Hopefully I won't give you a problem like that until I figure it out. But that is fair.
I'll wait until homework something like that.
Okay. Now, everything looks kosher, right? Doing it that way, where you combine those two reactions, just like that. But that's not right. It's not Kb. We did not determine Kb in that reaction. Right? We determined the reciprocal of Ka is all we determined. So that's what's got me questioning the validity of this approach. All right, let's move on, and I'll work on this one in my spare time.
well, why was it having us find the reciprocal of A anyway? Like, what was it trying to tell us that it did?
Oh, okay. Well, the forward reaction is this one.
Yeah.
But we need the reverse reaction. So the reverse reaction will be the reciprocal of that. Right? Just turn it around and flip it.
Okay.
So that's what they're saying.
All right.
And logically, okay, yeah, but we're still an aqueous solution, so you cannot discount water in this whole process. That's why I think this is probably an error. I need to dig into it a little more and come back to you with an explanation. Okay. So set that one aside for now. A scientist, I think he was Danish, or he might have been Swedish, can't remember what. His name was Sorensen. He was interested in hydrogen ion concentrations in acidic solutions, or basic solutions, whichever the case may be. But he didn't much relish the thought of using exponential notation to take 10 pages to do what he should be able to do in one. Right? So he invented this shorthand way of expressing hydrogen ion concentration, called it pH. Right? It was simply a mathematical transformation. He had the hydrogen ion concentration, or the hydronium, either way, and he took the negative log of it. Remember, and that's base 10. So what that means is, if you've got something in here times 10 to some power, then it's a simple transformation to use base 10. Right? For water, if it's 10 to the minus 7 is the hydrogen ion concentration in a neutral solution, right, like we showed earlier, then the log of that, base 10 is going to be minus 7, isn't it? Right? That's the way logs work. This is the value of 10 to that power. So 10 to that power is this. Right? But he didn't like using negative numbers either. So he stuck a negative out there, made it positive. So for neutral solutions, the pH, his value, his designation, pH is this transformation. Negative log of any concentration is P, whatever that
This
is.
is why when we go over 7, it's base and on down to the 7.
Yes, exactly. Less than 7 is acidic, greater than 7 is basic, because of this sign. Now, what do you do with significant figures? Well, in any log transformation, the number of decimal places in the log is equal to the number of significant figures in the original number. So if you have a number in here that's, I don't know, 3.25, then the the significant figures in your answer over here is going to be 2. 2 significant figures. That's just the way logs work. I've already wasted enough of your time, so just accept it. Because we have meters now that measure pH directly, and they'll measure 3 decimal places easy. So that's 3 significant figures. Okay. So you already got that one right. These are just some common items. Right? Vinegar is about pH 3. Lemon juice is a little more acidic. Stomach acid is more yet. Now, stomach acid can vary wildly. Right? This says 2, so I assume that's between meals. Right? When you eat your meal, the pH is going to go up probably for most meals because it dilutes out the acid that's already there. But when your body kicks in, starts making more acid, it should drop below 2. Or if you eat a meal that's rich in tomatoes, it's going to drop right away. Battery acid is even stronger. Right? What is battery acid? Sulfuric, right? And then 1 molar HCl is 0. So you can have a 0 pH. Right? Sorensen preferred between -14 and +14.
My brother had some hydrochloric acid in the garage one time.
Yeah.
He just cleaned off like rusty tools or something. I don't even know why he had it. But he found everything in the garage was rusted. And as soon as it got like taken out of there, if you don't put it in oil or something to coat it, it'll flash rust. And then it'll just cave up and rust. It's the worst. Everything in the garage is pretty much destroyed.
Yeah, you expose fresh metal, huh?
Yeah.
Plus, there's probably chloride vapors
Yeah.
in the air still.
Yeah, that's what it did. Like, I mean, there would be a shelf 10 feet away and it still just needed up.
Yeah. They call it muriatic acid. Use it to etch concrete too.
Yeah.
In fact, when I finished my basement, we built our house, it was exfoliating as the concrete cured. The surface would just flake, and the place would be covered in concrete dust constantly. Couldn't keep it down. So I said, okay, I got to seal this stuff, plus the concrete block. So I didn't do it on the concrete block because it was already rough. But the concrete floor was very smooth, and it wouldn't accept the stain very well. So you go in there with muriatic acid and hip waders and gloves and lots of ventilation, and you pour that stuff out there and use your brush and brush it in, and it will etch the concrete. Then you rinse it out with water really good. And then after it dries, you can go in and stain it, and it's rough enough, it will accept the stain and get down in the concrete, seal it good. Muriatic acid. But the pH of 1 molar HCl, so if you do that, take the log of it, like that. So, what value, power of 10, is equal to 1? Zero. Anything to the 0 power is 1. Zeros. All right, so negative positive doesn't have any meaning for 0. So you can have a 0 pH. It's just a simple log transformation. You can have negative values of pH. You can calculate them. But when you start getting into the negatives of pH, it really doesn't have much meaning. So what's the pH of this solution? Well, since that's 1, we really only need to be considered this one. Right? So 10 to the minus 4, the log of 10 to the minus 4 is minus 4 times negative minus 4 is positive 4. So the pH should be 4. This one is a little trickier because you have to convert it to 10 to the -2. Okay. So fortunately, our calculators, you can just plug the number in. You can plug it in like that if you want. But if you did that, what would you get? You wouldn't get pH, right? Because this is OH concentration. Okay? So, what do? Well, you got two choices. One that we know already and one that I haven't shown you yet, right? So we know that this one times this one is always equal to that one. Always. So if we plug in this one here, right, that one there equals this one, then solve for this one. So it's this one, 15 divided by this one. Right, so that's, let's see, 0.25 is this part. And this part is times 10 to the -12, which equals 2.5 times 10 to the -13. Now you can put that in your calculator, take the negative sign of it, take the negative log of that, and you can get your hydrogen concentration, which should be 12.6. Okay? Now, let's see. Okay, before I get to this is the long way. I'm going to give you the short way in a minute.
I got 13.6.
Let's try it again. .5, make it going 13, change the sign, log, change the sign. Yep, I got 12.6.
Oh, yeah, I got it. It looks like negative log.
Okay, now what if you have pH equal to 5.85 and you want to know what the hydrogen ion concentration is? If that's the pH, you need to take the antilog of that, right? You know what the antilog is? No, it's log. I mean, it's 10 to the power. 10 to that power is the antilog. But this is pH, right? And what is pH? Negative log. So if you want to solve for that, first you got to put this negative over here. Okay? Now, to find out what that is, it's 10 to that power. To the negative 5.85. That's what the antilog is. So on your calculator, you'll see the log key, usually. And then somewhere close to it, in mine it's next door, is 10 to the x key. And that's the one you use for this. You put in negative 5.85 and take 10 to the x for that. And let's see, what do we get? 10 to the -6. Okay. That's the hydrogen ion concentration at that pH. Okay? Now, before we had calculators, when I went to school, you had to do all that stuff using tables, log tables. All right, so we would have to take, well, in this case, we didn't look that up. It usually wouldn't be exactly the number, so you'd have to interpolate between two numbers. It was a real pain. Thank God for calculators. Okay, so pH and OH, how are they related? Let's see. So I erased it already. Here it is. 4 times 10 to the -2. 4 times 10 to the -2 was the one we had on that other slide. And that's always molarity, right? So many moles of hydrogen ions per liter, or so many moles of hydroxyls per liter. So watch this. This relationship is permanent forever. That's always true in any aqueous solution. So if we take the log of both sides, the negative log of both sides all the way through, right, we can do that, then the negative log of Kw here is equal to the negative log of the hydrogen ions plus the negative log of the hydroxyls, right? Because when you take the log of a product, you get the sum, all right? And since the sum has a negative sign in front of it, it's negative log this minus log of that. And that's also equal to this value, right? So here's the negative log of the Kw. There's the Kw. Here it is right here. So that's the pKw, right? If you take the negative log of anything that's in molar concentration, it's the P something. So pKw would be 14. And the negative log of this one would be 7, and the negative log of that one would be 7. So what we're saying is pKw equals pH plus pOH.
So it's the water water law or static log.
No, you just take the transformation, the log transformation, negative log of this, negative log of that, negative log of that. And what you get is, this is pH, right? Because that's hydrogen ion concentration. This is pOH, because that's hydroxyl ion concentration. And this negative goes into the P value. So it has to be a plus here. Okay? And this is the pKw. And the pKw is 14. So the pH plus the pOH is always equal to 14. So what we could have done was just take the negative log of that, 4 times 10 to the minus 2. 4 exponent. The log and negative. So 1.49. No. 40. 1.40. That's equal to the pOH. And since 14 is equal to the pH plus the pOH, then the pH is equal to 14 minus 1.4, or 12.6. Okay, so that's the fast one. Rather than having to calculate what the hydrogen ion concentration is and then do that, just do the one you got, subtract it from 14, and you got your pH. Okay? That's the quick way. So we would do the same thing here, calculate pH, subtract it from 14 and get 10. And because the pH of that is 4, 14 minus 4 is 10. And that was our 1.4 here. Okay. So if we have the pH of this and we want to know the hydroxyl ion concentration, we just convert that, well actually subtract that from 14. All right, so you would say 14 minus 5.85, which is what? 5. So 8 from 9 is 1, and 5 from 13 is 8. Right. Then we would take the anti-log of a negative value. And that would be 7.1 times 10 to the minus 9.
In other words, when we put 10
Do what?
then I got it. Get that in there.
Okay, when we have an acid-base reaction, where we got competing species, we have to consider these in, this is a good way to solve problems. What are the major species in solution? What you do is you just say, all right, just brainstorm. These are all the possible species that could be. And you just list them. And then you start logically eliminating the ones that cannot possibly exist. And those are your major species. Then you take those major species and say what reaction produced them, or what reaction, depending on whether they were reactants or products, what reactions are they involved in? And you write those reactions. And then you say which one of these reactions are reasonable, which ones are not, cross them out. Then you compare the ones that are left to see which one is dominant. Then you ask yourself, of those reactions that you're given, is this an equilibrium reaction, or does that reaction essentially go to completion? And if you have one that goes to completion, the best approach is to let that one go all the way to completion and then use the products of that complete reaction in your equilibrium expression to work your way backwards. So you need some examples. I know that those words just kind of go that. And then if it asks for the pH, solve for the pH. So let's take a simple one first. Let me do it on time. 10:45. We're in lab time already. I need to move it along. What are the major species of this aqueous solution? All right. So we know that HCl is going to completely dissociate. It's a strong acid, right? So there's not going to be any HCl in there. There will be chloride ions, there will be hydrogen ions, and there will be water. Those are your major species. All right. If those are the major species, and this is a very weak base, then the predominant species comes from HCl. Hydrogen ions do not dominate from H2O. And that being the case, and this is the case with all strong acids when you put them in solution, all you need to know is what was the original concentration of the acid, because it completely dissociates. In other words, it's not an equilibrium. It produces that many hydrogen ions. And then you can just straight calculate the pH. Okay, that's the simplest scenario when you put a strong acid in solution. Or a strong base for that matter. If you put a strong base in there, you just calculate the POH. And if the question is pH, subtract it from 14. So if we have a solution of, let's see, here, this is relatively concentrated and it produces a noticeably acidic solution. Right? But what if the concentration is extremely low? 1.5 times 10 to the minus 11 molar. All right. So major species, right here, HCl does not remain. So if we calculate the hydrogen ion concentration of that, take that as our pH, we actually produce a basic solution in that case. Okay, nitric acid, when it's added to water, what happens? That just completely blows apart. It's a strong acid. So the first reaction that takes place is nitric acid plus water yields hydronium plus nitrate ions. Why is this one not likely? Right? So once you produce those, what is it going to do? It's going to sit there. because it's a weak base, right? Strong acid produces weak base. So that's why this reaction does not occur. You can cross that one out. So which reaction controls the pH? Well, this reaction is always taking place. I've said that before. But is water the major contributor to hydrogen ions? No, not in this case, because you've got a strong acid dissociating and producing hydrogen ions. So what that says is that for this solution, the major species are these, and the source of the hydrogen ions is that concentration. And that's significantly larger than 10 to the minus 7th, is it not? Water by itself would produce 10 to the minus 7th. This is 5 orders of magnitude greater than 10 to the minus 7th. So the hydrogen ions produced by water are insignificant. This is going to be the dominant. This will dominate from nitric acid and produce that pH. Okay, so these are the steps that you would take. You can read those at your leisure. So let's say we have this situation. 0.8 molar aqueous solution of a weak acid. Here we go. There's our HCN, a weak acid. There's the K value for it. What are the major species? Well, what is this going to produce? Maybe a few hydrogen ions, maybe a few cyanide ions. Or to begin with, the major species are this. No. Right? It doesn't produce much in the way of hydrogen ion. So hydrogen, the protons and cyanide ions are not major species. The major species is this one and that one, and the K value for that is this one. The competing reaction is this one, the one that's always there, right? And its K value is this. So this one says that it's going to produce these species, even though they're not the major species, it's going to produce these species in excess of what water produces by 4 orders of magnitude, right? So this is our dominant reaction. This one controls the pH by quite a considerable amount, 10,000 times more effective. Even though it's a weak acid, it's still a stronger acid than water. So that's the one that we focus on. All right. We didn't do anything else with that one. That was just to make the point. When you're comparing those two reactions, you may have more than 2 reactions to compare, right? But in this case, we had that one dissociation of HCN, dissociation of water. We just compared the K values and found that the dissociation of HCN was the dominant reaction. How about this one? pH of 0.5 molar aqueous solution of HF. It's a weak acid, right? 10 to the minus 4. Right, what are the major species? Well, if it's 10 to the minus 4th, it's HF and water, basically. And then we compare, right? This one is a much stronger acid than water is, right? So this one is going to dominate. That one controls the pH. So now we set up our ice table. This is your first instance of ice with acid-base reaction. So if we have this reaction, then we have this is our initial concentration of HF, and we have a little bit of this, but not a significant amount. Right? So that we start off with basically 0, and that means that we're going to add X of this and add X of that and minus X of that. Why? Because it's 1 to 1 to 1. So this is going to be our equilibrium situation, and we can write our equilibrium expression in terms of those values. Here we go. So there's our hydronium, there's our fluorides, there's our HF. We just substitute those values in there. There's our X, X, and 0.5 minus X. Now, what we can also say is that X is going to be extremely small, right? Because the value is 10 to the minus fourth. That means that we're going to have such little over here that we can discount that X, right? And that's good. Otherwise, we'd have to solve a quadratic equation. Yeah, I got that. So now, all we have to do is multiply this times that and take the square root of it to find out what X is. So the concentration of X is this value, molarity. And let's see, what was the question? pH, okay, X is the hydrogen ion concentration, so we just take the negative log of that. And our pH is 1.72. Okay? Let's see. Oh, we want to prove, this is a proof of the validity of discounting that X value. When we had 0.5 minus X, we want to be sure that we didn't make a big boo-boo. So we use the 5% rule. And we take this expression and our complete expression and plug in the value for X for each one of these positions, calculate that value, which should be, this is the K, based upon our information, and compare that K to the true K, which is this one. Is it within 5% of that value? Okay, subtract this from that, divide by that. Yes, 3.9%, we're safe. That's the 5% rule. Now, what do we mean by percent dissociation? This is sort of analogous to the discussion from last chapter of equilibrium constant versus equilibrium position. Remember, equilibrium constant is constant. As long as the temperature is constant, equilibrium constant stays constant, no matter what the concentrations are. But if you disturb an equilibrium, it will shift to reestablish the equilibrium. Now the concentrations are different. You have a different position. Okay. Percent dissociation just says that you have an initial amount of acid, or base for that matter, and you have an amount that actually dissociates. So if you start off with this, and you produce that, then the amount of this that turns into that is the amount dissociated. Or we could say, if it, and it will be 1 to 1 to 1, this is the amount. Or this is the amount. Okay? And that's in molarity. It has to be in molarity, percent dissociation. So you take the initial amount you started with, let's do it this way. This is the initial amount. And this is the dissociated amount. Either one, because they're 1-to-1 relationship. So whatever concentration appears over here, divided by what you started with, times 100. That's percent dissociation. Now, what we've noticed is that for weak acids, as you dilute them, the percent dissociation goes up. It's counterintuitive. You would think that it would go down, but the percent dissociation actually goes up as we dilute the acid. Now, that doesn't mean that the concentration of acid increases. That means the ratio increases. So this amount will actually go down as you dilute it. But this also goes down, and this one doesn't go down at the same rate that this one goes down when you dilute. That's why percent dissociation increases. So here's how you would use that information. Say we have a solution of 8 molar formic acid, right, which is pretty substantial. That's concentrated. And if you've ever been bitten by a fire ant, you know what formic acid feels like. There's some other things. It's a cocktail, right? Formic acid is one of the ingredients. There's some other things in there. But they all have the same effect. They stimulate pain receptors very effectively. So if we start out with 8 molar formic acid, and we're given that it is 0.47% ionized in water, that means that its dissociation amount is 0.47% based on that previous calculation, right? So this is what we start with, 8 molar, and we don't have any of that. And we're going to convert this much. The change is we're going to lose this much, 0.47%, and as a decimal fraction is 0.0047. So we multiply that times that, and it reappears over here as a plus, plus there, plus there. Then we can calculate, this is what we end up here, this is what we end up there, this is what we end up there, calculate the K value. You just set up the formula, right, from the balanced equation, plug in the numbers, and that's your Ka. And all we needed to calculate that was the percent dissociation. So if we had that data before, we have this calculate the pH of the solution, we just need this value right here. Take the negative log of that value. Right? And our pH is 1.42. So it's fairly acidic, even though it's a weak acid. That brings up the point, when we say weak or strong in chemical terms, we're talking about the amount of dissociation. How much does it dissociate? Weak acids dissociate just a little bit. Strong acids dissociate completely, right? Now, as far as the corrosive effect of an acid goes, the actual number of hydrogen ions in that solution, the concentration of them, determines how corrosive it is, or how dangerous it is to your skin, right? So you can have a weak acid like acetic acid, but if you've got a bottle of glacial acetic acid, which is 100%, the number of hydrogen ions in there, the concentration is going to be high enough that you don't want to put your hand in it or spill it on. Because it might be a weak acid, but it can still do damage at that concentration. Okay? So weak and strong have a different meaning in chemistry than they do in the popular culture. Okay. So the value of Ka for a 4 molar formic acid solution should be what? Exactly right. Constants are constant. We call them constant for a reason. They don't change, right? As long as you don't change the temperature, K is going to be the same for both of those.
So is that the reason why if it's smaller, and then we have 8 molar right here, it will be the same?
Yeah, concentration doesn't matter, right? K is constant. Now, the percent dissociation would be greater for this one than for this one. The percent ionization, well, this is another way of saying it, percent ionization will be higher for this one than for the 8 molar. Think about it. It's an equilibrium situation. If you increase the concentration, you influence the reaction to remain. Well, actually, it's a dilution effect. That wasn't a good explanation, so set that one aside for now. Okay, so if this is our weak acid, And it dissociated, and we get a K value for it. Right. So we're saying that the concentration of HA left over is the initial concentration minus some amount of X. So what we're saying is this X is so small that basically the HA is the same as we started with. But we do produce some H plus and A minus. So our expression is going to be, for the initial condition, is this multiplied, squared actually, divided by the initial concentration. What happens if water is added so that HA becomes 1/10 as strong as this? Okay, so we're going to dilute it. The K doesn't change, but if we dilute it, what does that give us? Okay, now the new value of this and the new value of that are actually X divided by 10. That's we've disturbed the equilibrium, right? And the value of our new HA is also divided by 10. Right? Now that we've stressed the system by adding water, we reduce the concentrations of our products. Which way will the reaction go? All right, so we calculate Q. We've got this times that over this. Q now is 1/10 of our Ka, right? So if Q is less than Ka, which direction does it go? To the right. Right? If Q is smaller than K, that means the products have been decreased relative to the reactants, and it wants to go toward products. So it adjusts to the right, which means that our dissociation percent goes up, right? Because we've taken a ratio at this level, and we've taken more now of this with less of this, and we get an increase in the value of percent dissociation. So what does that mean? That means the pH of the formic acid solution, of the 4 molar formic acid solution, is going to be higher. Right? We may have changed the percent dissociation, but we decreased overall the concentration of hydrogen ions. So the 4 molar formic acid solution, even though we increased its dissociation, is going to be a higher pH. It's going to be more toward the base than the 8 molar. And we can calculate what that is, right? Because now we know what the K value is, and we can plug in our values here, right? And we can find out that X equals that, and the negative log of that. Oh, calculate the percent ionization. Okay, so this is, we calculate the percent ionization. We're going to find out that it's 0.67 rather than 0.4 or something, wasn't it? So percent ionization is increased, but what's the pH? Right? Come on. There it is. So instead of 1.2, now it's 1.57. Okay, how about bases? Well, strong bases, lithium, sodium, potassium, calcium, even calcium is a strong base. But if you look in your useful information, I don't know if we have that with us. I didn't include that. The solubility. No, I didn't. Solubility of calcium hydroxide is very low. Right? So when you produce calcium hydroxide, it's going to drop out of solution and leave just a tiny amount in solution. But chemically speaking, whatever is in solution is dissociated. So it's a strong base. Okay? So there's a technicality. Chemically speaking, it's a strong base, but it's just not very soluble. Right? Whereas KOH, sodium hydroxide, and lithium hydroxide, those are all soluble. So if you've got some of those, they're all in solution. All right. So there's our pH of this solution. Right? We used our handy dandy 14 minus. So how about calcium hydroxide, the pH of a 1 times 10 to the minus third molar solution. So what we're saying there is that even though it's insoluble, this much of it is in solution. So we can calculate the pH based on that much that is actually dissociated. Right? The thing about it is, this is the concentration of the whole molecule. But for each one of these, you've got 2 hydroxyls. So the hydroxyl concentration is double that. And then the negative log of that gives you the POH of 2.7 and a pH of 11.3. Right, so pay attention to the stoichiometry of that reaction. Because for every 1 calcium hydroxide, you get 2 hydroxyls. Okay. So this would be a strong base from a weak acid. Right? And that's the expression for it. So anytime you have a Kb, what you're looking for is the base plus water producing the conjugate acid plus a hydroxyl. Right? So if you see a hydroxyl on this side, you should be looking for a Kb value, not a Ka. All right. So I'm going to set those aside for now. Polyprotic acid. Okay. Generally speaking, in fact, this is true for any polyprotic acid. What do we mean by that? An acid that is able to produce more than 1 proton per molecule. Right? So like I said before, if it has 2 or more hydrogen ions available, the reaction takes place 1 at a time. And the first one is going to be a stronger acid than the second one. Right? For instance, phosphoric acid. Phosphoric acid will dissociate, produce that proton plus this conjugate base. Okay? And it will have a K value. This one can also dissociate to produce another proton. And its conjugate base is that species. And it has a K value also. Got 1 more proton left. So we can take this one, dissociate that proton, and gives us that. It's K. Okay? Numerically speaking, this one is always larger than that one. And this one is always larger than that one. Think about it this way. That's a neutral atom, right? So it's easier to pluck a proton away from that neutral. Now you got a charge. It becomes more difficult to extract a proton from a charged species. And then this one's got a double charge. It's even harder to get that last one away. So that's why this one is smaller than that one, and that one is smaller than this one. So in solution, actually, this reaction dominates because the difference between each of the Ks is several orders of magnitude difference. smaller, by several orders of magnitude. Now, it will still produce some of these and produce some of those, but not very much. Well, the dominant reaction, the pH controlling reaction, this one. Yep. Okay, so here we go. So this one is 5 orders of magnitude smaller, and this is another 5 orders of magnitude smaller. And so the controlling reaction is the first one. There's your second one, I think. That one, no, okay, here we go. This is the first one. Right, so if we solve for X in those terms, for a 1 molar solution, oops, we missed the 5% rule, so we're going to have to go back and do it by, and we could either use quadratic. I think in this case I use successive approximations. Have we talked about that one yet?
I don't think so.
Okay, instead of using the quadratic, you can take the value that you get from the first calculation, plug it into the X value that you discounted originally, and then solve for those other 2 X's in the top again. And that gets you closer. By successive approximations, it may only take once. Right? In this case, it really only took once. 5% rule should be satisfied. Right, there it is. So, but sometimes you may have to go 2 or 3 approximations, and you just take your new value and plug it back into that old position here, this position right here. That's the one we discounted before, but if we take our first calculation and plug it in here, and then go through, find out what X is, we find that we're close enough now. So instead of using quadratic, you can use successive approximations if you want. Okay, so calculating the pH means that this one is the dominant one, and the pH is 1.08, in this case, 1 molar solution. But suppose we want to find out what this concentration is. Well, we can take our second one and set up our ice table, and we do have this amount right here, and we do have this amount. Without that, calculate what X is. Right. And that gives us this concentration, which is basically what we started with for hydrogen ions. But it also gives us the concentration of our HPO42 minus. And if we go through the third K value with that value intact, and this new value for our HPO42 minus, which was derived from this one. Because remember, that one doesn't change. If that's initial, that's where it sits for weak acid. Then we can calculate what PO43 minus is. And it's very, very small, 10 to the minus 19. So you really don't have much phosphate ion in that solution. Okay, what are salts? Well, salt in popular culture is a different definition than salt in chemistry. Salts are derived from the reaction of an acid and a base. So if you have an acid, let's use a real world example. Say we have hydrochloric acid, and we're going to react with sodium hydroxide. Right? There's our acid, there's our base. Now this is not just dissociation of an acid where you have produce a conjugate base. This is a reaction of an acid and a base, and if you treat it as a double replacement reaction, just this swaps places with that. Right? Sodium swaps places with hydrogen. That means sodium and chlorine come together. and they're soluble. And then what do you have left over? This hydrogen goes over there to the hydroxyl, and what do you get? Water. Okay? So in an acid-base reaction, you have acid reacting with a base to produce water. Chemically speaking, there's your salt. So that's the format. Acid base produces salt plus water every time. That's the chemical definition of a salt. And salts, they can either be soluble or insoluble. In this case, it's soluble. And you've got a cation with an anion, at least one of each, depending on the stoichiometry and the formula. So, back up. There we go. So, what happens? Now we're interested, once we define what a salt is, it's a cation with an anion. Suppose we have cations and anions that can be derived from different sources, not just these sources. If the anion is derived from a strong acid and the cation is derived from a strong base, then if you take this, put it in solution, you get a neutral solution. Strong acid, strong base origin for salt gives you a neutral solution. Okay, every time. But what happens if you have a salt that's derived from a strong acid and a weak base? Let's see. Okay, hold on a second. I want to be consistent with my slides. So the conjugate base is strong. And conjugate acid is weak. Examples of that. Right, sodium. Sodium is derived from a strong base, sodium hydroxide, K, potassium hydroxide. So this would be sodium, potassium examples. And this one would be fluoride or acetate. Okay. So these are derived from a weak acid. These are derived from a strong base. Okay. If that's the case, then the solution is going to be basic. Other way around. If we're deriving our acid from a strong acid and a weak base, the solution is going to be acidic. When you dissolve the salt, right? If the salt was derived from a strong acid, weak base, then the solution, if you just take the salt and dissolve it, you get an acidic solution. Right? If it's derived from a strong base and a weak acid, then you get a basic solution. Now that's the rule of thumb. Right? Weak acid, strong base yields basic solution. Weak base, strong acid yields acid solution. What if they're both weak? Well, then you have to know exactly what their K values are. So that takes some calculation. All right. So if your cation anion is well, whatever you know that. Sodium chloride, that would be strong. I would have said strong, and the acidic, and then the solution is neutral. So that should be strong. If the anion is a conjugate base of a weak acid like fluoride, then you get a basic solution. So strong, weak is basic, weak, strong is acidic. And if you have weak, then you compare the Ka and the Kb values to determine what the final solution is. Theoretically, it could be neutral, but you won't know that unless you compare the Kas and the Kbs. Okay, so if we calculate the Kbs for each one of these, right, we just need to divide that into 10 to the minus 14 and divide that into 10 to the minus 14. We can find those values for each one. Oops. Jumped on. There we go. Right. Then we find that this is a stronger base than that. So when we combine, well, that's, okay, that doesn't work. You're not going to get a salt out of that. Why is that up there? Oh, that's so we can compare these. All right. How we doing on time? Running out of. So what we want to do here, let me see. Let me check our schedule. I've built in anything for this one. Oh, next week is spring break.
Yeah.
And we got to get these both done today because I don't have any buffers built in. All right, so we two approaches to this one. To order these from lowest to highest pH. So which is the most acidic? Right? We can do it qualitatively. And examining electronegativities and acid-base strengths, then we can make some approximations. First, look, are there any compounds composed of ions from strong acid, strong bases? Strong, here we go, sodium chloride, strong acid, strong base. Okay, so that one go right in the middle. That one's neutral. Right. So if we've got 1, 2, 3, 4, 5, 6, 7, 8, 8, I've determined that number 5 puts it in the middle. Are there any strong or moderately strong bases? From lowest to highest pH. So the highest pH would be the largest number. Sodium hydroxide. Yep, sodium hydroxide. Right, so that's a strong base. Right. Ammonium will have the next highest pH. So sodium hydroxide will go all the way over to the right. We're doing pH from low to high. And then pH increase, decrease. Right. So then we have ammonium. Ammonia will be the next one. And then we have right in the middle would be our sodium chloride, because it's neutral. So it's pH 7. Okay. Now, Are there any compounds composed of ions from weak acid, strong base interactions? Weak acid, strong base. So there's a strong base, weak acid. Right. That's definitely one of them. And it's going to be over here. So this one, there. Are there any acids derived from halogens? Halogens are going to be, some of them are going to be strong, except for this one. So this one's going to be the strongest acid of the bunch. Yeah, so this one would be there, and the next one would be this one. Right. And then what do we have left over? We have ammonium chloride and HCN. So we're competing between this relatively strong base and this extremely strong acid. So I would say this one would be more acidic than basic. Right? So we're going to have this one in here, and we're going to have this one in here. It's just which one comes first. So it's also weak base, strong acid. Closer to the basic than weak base, strong acid. Closer to the basic than the HCN. Right, because this is an actual acid and this one is the salt. So that's why we're saying that HCN is very likely more acidic than NH4. So this order is probable. We're pretty good with the rest of them. This is the one where we might need some quantitative information. But we need to know the Ka for this, which is 10 to the minus 10, and we need to know the K for this reaction. Right, so if we do it quantitatively, we look at the Kas and the Kbs. Right, so this is the Kb for the Cn minus. This is for the NH. Yeah, it has to be for this one. And this one is the strong base. So we're just looking at the comparison of these two and find that this one is a stronger base than that one is. Right, so that's why this one pushed that direction. No, wait, excuse me. Oh, that puts it over here. Excuse me. No, that's wrong. We want to compare this one and this one. Those are the two we want to compare. Right. So this one is a stronger, slightly stronger acid than the K for this one. That really shouldn't be a Ka. It should be K guide. If it's H something, then it's a Ka. If it's salt, it's just a K. All right. So we have a solution of 0.3 molar sodium fluoride. The Ka for HF is that. What are the major species? Okay. Well, let's see. It's a soluble salt, sodium fluoride, so it's going to be completely dissolved in water. So you're going to have sodium, and you're going to have fluoride ions. Right? And you're going to have water. So these are your major species. How do we get that? This is completely soluble. Right? So these are the major species that you're starting with. And I just threw those in there because that references the fluoride ion. All right, so what are the possible reactions? Well, that fluoride ion could react with water. Right? If it came from a weak acid, then it's going to be a strong base, the fluoride ion. Right, so that's valid. Water, that's going to be there. It's always there. Sodium and water. Are we going to get that reaction? No. So we're going to throw that one out. We're not going to go backwards, right? This is not a reaction that's going to be doable because this completely dissociates from water. So it's not going to be an equilibrium situation at all. Right? So those two are gone. We're really only comparing the top two. So we want to see which one is the more favored reaction. Which one controls the pH. Right? So if we look at the KB for this one, because that's the reaction here that would drive it that direction, and the one for this one, KW, oops. Okay, the KW is 10 to the minus 14, which means this reaction is favored by a factor of 1,000. This is the controlling reaction. Right? So calculate the pH of a solution in which we start off with sodium cyanide. Oh, that was an exercise in deciding which one was favored. Right? So we decided based upon their K values, and we had to use the appropriate Ks. One was a Ka or Kw for water, and the other was Kb for fluoride. What about this one? 0.75 molar solution of sodium cyanide. So the Ka for HCN is this, but we're probably not interested in that because we're starting off with just the cyanide ion, not with the hydrogen cyanide. Right? So the major species would be this that we're concerned with. Those are possible reactions. Get rid of the two that are ludicrous. And now we compare these two and see which one is favored. Okay. So if this one, which reaction controls the pH, right? The Kb for this reaction would be 1.6 times 10 to the minus 5. Right? So it's much stronger than water, and that's the controlling reaction. Right? This one. That's what we start with. We got virtually none of that. And we end up with this is our equilibrium expression. Plug it in. We're going to say the X is, throw the X out. We have to decide if that's true. Right. There's our POH. There's our pH. Oh. Okay. So I guess we have to take your word for it. But you can calculate whether it satisfies the 5% rule. I assume it does since we didn't bother to calculate it. Okay, what controls the acidity in a binary compound? What makes one acid stronger than another one? Two things. What's the polarity of the bond? If the bond is extremely polar, then you favor, and I'm talking about the bond between the hydrogen and some other part of the molecule. Right? So if it's extremely polar in that direction, then it is extracting electron density from the hydrogen. And remember, this hydrogen is going to leave as a proton. So the more electron density we can extract from the hydrogen, the easier it is to leave. Okay. High is good. Bond polarity, high is good for strong acids or for stronger acids. Bond strength. So if the polarity, well, the polarity is one item, but if the bond strength is very weak, then we also get a stronger acid. So low bond strength, high polarity, and these are interrelated actually. Two ways of measuring similar effects. So if we looked at it in terms of bond strength, right? So here's the bond strength for HF, and it decreases for HCl, HBr, HI. So we get increasing strength as the bond strength decreases, the acid strength increases. Now that's for binary acids. for oxyacids, which have a hydrogen, and then we have something here with an oxygen. They could have more than one oxygen, right? Like, how about this one? The series of right? Perchloric acid, chloric acid, chlorous acid, hypochlorous acid. Right? So how does the strength vary? And the only difference is the number of oxygens. Right? So the strength of the acid increases with the number of oxygens. So the acid strength increases with the number of oxygens. Why is that? Oxygen is an electronegative atom, right? It's way up here. Chlorine is electronegative. If we add more and more and more oxygens, they tend to extract electron density, make it shift away from the hydrogen. So the more of them you have, you weaken the bond between the chlorine and the hydrogen. So as you increase the number of oxygens, you decrease the bond strength and increase its acidity. So perchloric acid is very strong acid.
If you had like a bunch of fluoride, then it would eventually be a strong acid too.
If you put fluorine in here instead,
Yeah,
it doesn't happen.
it doesn't happen that way.
No, because fluorine in this situation does not form that series.
Oh, okay.
Yeah, I think I have blurb on it. Oh, maybe not. Right, so here's some others, right? SO4 and SO3. Right? SO4 is a stronger acid than SO3, the sulfurous. The nitric vat versus nitrous, it's stronger than this one. Here we go. Why not HOF? So if we look at the electronegativities of each of these, right, we find that the electronegativity of the chlorine is stronger, and the Ka is also stronger with that oxygen in there. Now before, when we didn't have oxygen, it's the other way around, right? But when we had the oxygen interspersed in here with just one oxygen, then we find that the electronegativity of this means that the strength of the electronegativity wins out over the effect of the oxygen.
So would HOF be?
Doesn't exist.
Oh,
Why? HOF decomposes at about 0 degrees in water. Form HF and H2O2. It makes hydrogen peroxide and HF. Right. So it really has no meaning because it decomposes. And I think it decomposes because the fluorine extracts so much electron density from it that that bond right there is very weak. So what happens is it decomposes into that and that. And then you get two of these together to produce hydrogen peroxide. And then an extra H from somewhere. That's not balanced. But that's the logic anyway. It decomposes. I left water out. It reacts with water. Now, what other types of acids are there? Or what other types of acid bases are there? Well, remember we said originally that acids and bases could not be described in terms of protons or hydroxyls being produced. You have to think of them in terms of hydrogens either being donated or accepted. And this is another example of that. For these acid anhydrides, the bound with oxygen, some element bound with oxygen. And these elements are always nonmetals. SO2, NO2 in this series, CO2. So the O2s here are good examples, form acidic solutions. And we call them anhydrides because they readily hydrate in water, producing acidic solutions. So in this case, SO2 gas, which is very smelly, bubbles through water, produces sulfurous acid. It reacts with the water, right? And any one of these react with water. When they bubble CO2 into your pop, CO2 gas bubbled through water produces H2CO3. Right, so it's carbonic acid. Okay, produces an acid by reacting with water. Now, why does it pop? Because it really wants to be in this way. Okay. It produces that, yeah, that's true. But the equilibrium is toward the gas. So when you release the pressure on that 2-liter bottle, it pops.
So carbonated water would be kind of technically some kind of acid.
Yeah. Mm-hmm. Oh, yeah. Carbonic acid. Now, they add other acids in there, too. They add phosphoric acid, maybe a little bit of lactic acid, depending on the drink, for flavor, largely. Then we have the basic anhydrides. They are oxides of metals, like potassium, calcium, these guys over here, sodium. When they react with water, they produce the hydroxyl. Okay, so they produce the basics. The acid anhydrides are the nonmetal oxides, and the basic anhydrides are the metallic oxides. So basic, acidic. Now for the concept of Lewis acid base. What G.N. Lewis discovered was that he couldn't fully describe his reactions in terms of whatever existed at the time. And he found that acid-base chemistry descriptions were insufficient for his. So he expanded the definition of acid bases and eliminated the proton transfer concept and instead discussed acids and bases in terms of electron pair transfers. Right. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Right. For Bronsted-Lowry, the acid was a proton donor. So when you donate a proton, the acid accepts the electron pair. So how does that work? Well, like this. Right? So there's our hydrogen and chlorine bound with a pair of electrons. Right? So in the Bronsted-Lowry definition, it donates a proton to something. But in the Lewis definition, it accepts an electron pair, right? Because each bond is 2 electrons. Right? So the Lewis definition incorporates Bronsted-Lowry, but it also allows us to conduct acid-base reaction in non-aqueous solutions. And for organic chemistry, sometimes that's essential, because water is so reactive in some situations for organic chemists. You don't want to conduct your reaction in an aqueous solution. It's an interfering reaction. You want to eliminate water from the reaction, but you still want to conduct the reaction as an acid-base reaction. And the only way to do that is as a Lewis acid or a Lewis base. Okay, so there's our relationship of the three models. There's our summary. So that's chapter 14. I guess everybody's been sort of taking a break as required, or a nap as the case may be. Okay, so let's get through this. Chapter is shorter, but we should be able to get through it before we run out of time, I hope.
Took them 30 minutes,
30 minutes?
I think.
All right.
Well, yeah, we leave it like 12:10.
3. Okay, so let's call the next one up and get this show on the road. So the next chapter, chapter 15, primary focus is buffers. That's where we're headed with chapter 15, discussion of buffers. They say acid-base equilibrium, but we've already been introduced to it. Wet the whistle. Okay. So, as far as Zumthal is concerned, the acid-base equilibria, their focus is on buffers. Right? So we need to discuss a couple of things before we actually define what a buffer is. So let's start with something we know, Le Chatelier's principle. If we have a reaction, and this happens with acid-base reactions or any other type of reaction, it's called the common ion effect. We can shift the equilibrium if we add an ion that is part of the equilibrium reaction. Right? So if we say, I'm trying to think of one that we did last week. A reaction. Okay, let's take the very simplest one. The first one we did.
So this is like the one of the lab ones.
Yeah, yeah. The solubility of sodium chloride. Okay? So if we're in equilibrium here, and you have your sodium chloride solution, and you added a strong hydrochloric acid, right? So there's not enough water in there to dilute it out. We did both. We did a strong HCl, we did a weak HCl. But our strong HCl produces hydrogen and chloride ions, right? So there's our common ion. We added this to the solution. That added this, which shifted the reaction toward the solid, and you saw precipitation, kept cloudy. That's the common ion effect. And it can be simply just adding an ion to an equilibrium situation, or you can couple reactions which have common ion between them and influence the equilibrium that way. One other way we added, well, actually, let's not go there. I'm starting to stir up the bottom of the creek with a stick and it's getting too muddy. Okay, so here's another example. In this case, we've got HCN, our weak acid, right? If we add sodium cyanide, then what's the common ion? It's the cyanide, right? So if we add sodium cyanide to this one, it's going to shift the equilibrium back toward the undissociated acid. That's the common ion effect. Now, what's a buffer? Well, we can measure pH, right? Hydrogen ion concentration, convert it to pH. If we want to maintain a pH that's within a very narrow range, particularly for biochemical reactions or ones in which living cells are involved, because they're extremely sensitive to changes in pH, then we can create a solution that holds the pH relatively close to a fixed number. It won't be fixed, it's not a constant, it won't stay there, but it won't drift very far. Right? That's our buffer. And it's said to be buffered at or near a certain pH. And it nearly always involves weak acid or weak base containing a common ion with some strong acid or strong base, as the case may be. Okay. Most buffers are built from weak acids and their conjugate bases, but not all of them.
When adding a strong acid to a buffer, the acid first ionizes in the aqueous solution. As hydronium ions are added to the buffer, the equilibrium shifts left, according to Le Chatelier's principle. Initially, in this acetic acid acetate buffer, there is a new acetic acid molecule formed for nearly every hydronium added to the solution. As the added hydronium ions react with acetate ions, equilibrium between acetic acid and acetate ions is reestablished. Only a very small amount of acetic acid ionizes to form acetate ions and new hydronium ions. The animation illustrates this process. Here, a hydrogen chloride molecule ionizes in water. The resulting hydronium ion reacts with an acetate ion, forming acetic acid. Due to the small Ka of acetic acid, very few acetic acid molecules ionize to form acetate and hydronium ions.
Okay.
A buffer solution, like the one on the right, resists changes to pH upon addition of small amounts of acid or base. Each solution here starts at pH 9.25. The solution on the left is not a buffer solution. Click the button to add the strong acid HCl.
The non-bucket solution changed drastically, whereas the bucket solution changed just very little bit. Well, this thing opened it. Okay. So, if we have a weak acid that's part of the buffer situation, reacting with water, and it produces conjugate base and the hydronium. And now we're at equilibrium. If we add hydrogen ions to this situation, what's going to happen? Well, if we add hydrogen ions here, in the form of hydroniums, of course, then the reaction is going to shift back this direction. And notice, with this weak acid, that's a strong base. A strong base will attach itself to protons readily. So almost everything we add here is converted back to that. Right? So that means the pH does not change much. So what if we add base? Right? So what would our base be? Well, let's say hydroxyls. So remember, everything here is in solution. Okay? So what is our base going to react with? Well, our base is going to react with hydroniums and produce, actually, 2 waters. Right? Because, remember, what's the KW for that dissociation? It's 10 to the minus 14. So this is an extremely strong base, OH. It will attach itself to hydrogens readily. So here's what it does. It reacts with these two to produce that, and it goes back this way. So when it does that, what happens to the equilibrium? It shifts that way and produces enough hydroniums to rebalance and reestablishes very close to the same pH it had before. So when you add acid, they react with the conjugate base, and when you add base, it reacts with hydronium to stabilize. That's in a situation where you've got a weak acid as the foundation of your buffer. You can make a similar logical explanation for a weak base buffer. But it all has to do with either a common ion here or the reaction of the hydroxyl with that ion. Okay. There were a couple of researchers, Henderson and Hasselbalch, who wanted a quicker, easier way to establish buffer pH and help them design buffer systems easily. So what they discovered was, if you take this dissociation of your weak acid, that's supposed to be an arrow. You have an expression here. Your Ka for that weak acid is products divided by reactants. So you've got that as established as your baseline. So what are we going to do with it? Well, Henderson-Hasselbalch reasoned that if they wanted to calculate the pH, they needed to get this hydrogen on one side of the equation. So they kept it here, and they took this one and put it on that side, which inverted it. Okay? So now it's inverted on that side, and since it's an equivalence, we can just swap places with it. Right? So this was over there, and these were over here. We just swap places. So now we have hydrogen ions equals the Ka of the acid times this ratio. Now, if we're going for pH, we need to take the negative log of the whole equation. Right? So if we take the negative log, this side will be pH. And the negative log of this would be pKa, right? And then we want to leave the negative log of that alone because these two values vary. So we don't want to resolve that one. We don't want to say P blah blah. It just wouldn't make any sense. So that's what they did. They took the negative log of both sides, okay, gave them that equation. But nobody likes negatives. It's kind of like scientists don't like curves either. They like straight lines. So we're going to get rid of that negative. So how do you get rid of a negative in a log expression? You invert the log. So if we take this one, put it down here, and this one put it up here, that becomes positive. That's just one of the log rules. So now, this is the Henderson-Hasselbalch equation. If we we want to find out what the pH is, we need to know the pK of the weak acid, and we need to know the concentration of the weak acid and its conjugate base, and that ratio. If we know that, then we can calculate the pH of our buffer solution. Okay? Oops. There we go. So the interesting thing about this is the only thing, the primary determinant of the buffer pH is the ratio of the conjugate base to the acid. So they can be any concentration you want, as long as this ratio is maintained, then the pH won't change. What does change is the buffer capacity. If this value is large and that value is large with the same ratio, then you have more capacity because of the reaction that took place here, right? If you use up something, right, you've got plenty more to take its place. So the buffer capacity increases with concentration. But as long as the ratio stays constant, then your buffer pH will be maintained. So what's the pH of a buffer solution that's 0.45 molar acetic acid, 0.85 molar sodium acetate? So here we have established this as our acid concentration, the HA, and this as our conjugate base concentration, and the Ka for acetic acid, well, sometimes it's 1.7 and sometimes it's 1.8. So it just depends on the author. So if we plug them into our Henderson-Hasselbalch equation, this concentration is here, this concentration is here. The negative log of our Ka goes here, right, pKa, and then resolve that to a pH of 5.02. Now what we could do is establish these as starting positions and do an ice table, and you would end up with exactly the same pH. All right. So I've already showed you this one on the board. If you add acid, it reacts with the weak base, reacts with this one. If you add OH, it reacts, well, it says with the weak acid. But I personally think it reacts with the hydronium ions. But you get the same result either way, whether it reacts with the hydroniums or it reacts with the HAs. Okay, so what would be the ideal buffer pH for our solution? Well, based on this definition here, we want plenty of these around, right, to react, but we want plenty of these around too, right? So what's the ideal ratio for plenty of both? Equal amounts, right? If you have equal amounts of A- and HA, then you will have enough of either one to resist an acid addition or a base addition. And what that means is the ratio here between the two would be 1, and the log of 1 is 0, right? 10 to the 0 power is 1. So this term drops out for the ideal buffer where that ratio is 1 to 1, and in that case, the ideal pH is the pK. All right, and we're going to use that fact next week when we do our lab. Well, not next week, the week after. Right, because next week is break. So the week after, when we come back, we're going to determine the pKa experimentally for acetic acid using a pH meter, and we're going to titrate and draw a titration curve and find out what that, for that pH, is equal to the pKa, and then we can calculate the Ka from the antilog. The method, I think, has pretty substantial description of what's going on. Yeah. So just study that. And we'll do a review, and then we'll follow it up with any problems that you might have understanding what we're going to do in the lab. But you should have it in your notebook. Yeah. So the buffer capacity refers not to the ratio, but to the magnitude. Right? So if you increase this one to a large amount, then this one also has to be increased to match it, that ratio. The problem with large buffer capacity for biochemistry or living systems is they can only stand so much, right? And you get an effect, a salt effect, an ionic strength effect. When you increase the ionic strength past a certain point, you start denaturing proteins, and that kills cells. So you're limited in living systems how high you can make that buffer capacity, right? And there are recipes galore for making buffers. Some of them use multiple anions, like phosphate buffers. We'll have phosphoric acid, they'll have HPO4 minus, H2PO4 minus, HPO42 minus in there in a certain ratio that establishes a buffer pH at a reasonable ionic strength for your living systems. Okay. This is just for information purposes. It's not really, I don't think I have any problems in the review that you need. But the buffering capacity, signified by this capital beta, is delta N divided by the delta pH. So what is delta N? That's the change in normality of the acid or base. So this is actually a measurable value. So it doesn't matter what your buffer is, you can get a buffer capacity by titrating an acid or a base and measuring the pH. And just whatever the change in normality produces a certain change in pH, you can calculate a buffer capacity. Right, so that's the quantitative approach. I was giving you a qualitative expression of what buffer capacity is. This is actually how you do it. Okay. Let's see, choosing a buffer. Right. I mentioned this earlier, right? Your ideal buffer pH is the pH at the pK. Right? So if we take, let's see, what was the pK for acetic acid? It was 1.8 on the slide, times 10 to the minus 5th. Right? No, that's the Ka, excuse me, that's the Ka. So the pKa is equal to negative log of this value, which is 1.8 times the log of that, 4.7. So that would be the ideal buffer pH for a buffer based upon the acetate ion. 4.7.
So that's one buffer.
Mm-hmm.
So that's the.
Well, that's how you would choose the buffer, based upon its pK of the weak acid. Okay. Let me look at my hard copy and see how much more we got to go. I don't want to run out of time. We got 10 minutes. All right, so we're going to have to move along. I just want to make one point. The equivalence point is the stoichiometric point where the acid and the base that you add together in a reaction exactly equal one another. That's the equivalence point. Sometimes it's more convenient, though, to use a color indicator, like we've done before with phenolphthalein. And that gives you an indication that you're close to the equivalence point. Right? The reason it's easier to deal with is in order to determine the equivalence point, you need to do a pH curve of the titration. Produce that S-shaped curve. The equivalence point is right here. Buffer zone is right here. And this is added base for a weak acid. Right, so this one would be our 4.7 right there. This one would be a different pH. And the middle of that, the inflection point of that curve from concave up to concave down is the equivalence point at that amount of base. So you want to pick a color indicator that changes color very close to that region. That way, you can just do the titration up to the color change, you're done. You don't have to take successive measurements to find out exactly what it is. And believe me, the error of using an indicator, if you use the right indicator, the error is minuscule. So if you have hundreds of titrations to do, you may do one titration curve to find out where the equivalence point is, and then pick your indicator, and then go with the rest of them.
But I know if I'm just not doing it, my graphs.
You do. You have to draw this one.
Oh, yay.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
Okay, so there's your equivalence point, or your the exact. So if you have strong acid, strong base, the equivalence point is going to be at 7. Like we said before, when you put those two together, you get a neutral solution. If you have a strong base and a strong acid, go in this direction, same thing, pH 7. But when you're dealing with a weak acid and a strong base, you need to break it into two parts. The stoichiometry, where the reaction goes to completion, and then you work your way back with an equilibrium problem. All right, so let me see if I can illustrate one. So here's your weak acid, there's your strong base. Okay. So what are the major species? Those are your major species. This one is not dissociated very much. This one is free, this one's free, and you've always got water. Right. So what are the possible reactions? You got your water reaction, you got your HCN and water, HCN and hydroxyls, sodium hydroxyls. And of course, those two are ludicrous, so they're gone. So what are we going to do? Well, what we're going to do is we're going to, if we're doing a titration with a base and an acid, we're going to use this one to go to completion and find out how much this one we have at the end. Then we're going to use this one as in our equilibrium expression. All right, so now that we have the reaction going to completion, we set it up to, oh, we didn't do the reaction. It was just, okay, it's one of those what ifs. Right. So here we have acetic acid and sodium hydroxide. Maybe it'll let us do one here. Those are a major species. Those don't count. So which reaction controls the pH? Well, there's this one. Nope. This one, yeah, it's a stronger reaction. this one, the strong base will react with the strongest proton donor here. So actually, in this case, since this one is combining with that one, this is the controlling reaction to begin with, producing this much, right? So this one is the one we let go to completion. Right, so there's our completion reaction. This one reacting with that one. So at equilibrium, we have this one and this one that have to be put into the, actually that wasn't the equilibrium. That's a misnomer. This should be completion, initial change completion. Now we have the equilibrium reaction, right? Once we've established how much of this was produced, how much of this we start with, then we can do the equilibrium reaction and calculate the pH. Now, you want to do it quicker? Henderson-Hasselbalch. We know what this one is. See, if we do the first reaction to find out what these species are, this one and this one, then we can plug it into Henderson-Hasselbalch and we're done. So we don't have to do the traditional ice table. All we need is the I part to find out what this is and that is from our previous completed reaction. Then we can calculate this. Right. So there's another example. Let's see. We want to do, I want to get to indicators. So this is an indication of the equivalence point for various acids. Strong acids are going to give you this H7 in the middle. Whereas as the K decreases, your equivalence point moves up. So -2 would be up in here, -4 would be up in there, -6 would be up in there. But it moves on up as the K gets smaller. All right, acid-base indicators. Acid-base indicators are a simultaneous reaction. An acid-base indicator undergoes either protonation or deprotonation as a reaction. Add a proton, take one away. The protonated form has one color, the deprotonated one has a different color. So as you add protons, the indicator is sitting there going through its reaction, and there's just a little tiny amount of it, so it doesn't interfere with your reaction. It just takes a couple of protons as you add them or as you subtract them, and gives you a pH at which that color changes. And it all depends on the Ka, right? So a loss of a proton in our phenolphthalein makes it go from, let's see, basic is pink, right? So loss of a proton means pink, gain of a proton means clear. And the pK gives you the indication of where that value occurs. And we can do a calculation here and say the ideal range of pH is pKa plus or minus 1. Right? So if its pK is 9.4, this ideal range is going to be 8.4 to 10.4, right in there. And then you've got lists here with colors. Those are all possible indicators. There are a host of others. But you can use a chart like this to tell you where's the ideal pH for your indicator. Very simple. Okay. So we'll see you next Monday.
Not next Monday.
No, week after Monday. Good. Yeah, I need that week. I don't know about you. I need that week bad.
I'm working on homework, so